All right, in this part of the lesson, we're going to look at something called enthalpy, which is denoted by the delta H. And why that's significant is because I think of enthalpy, I think of heat, because enthalpy is defined as the energy absorbed as heat during a chemical reaction at a constant pressure. So one thing to note is we can really only measure changes in that enthalpy. There's not really like a standard zero enthalpy, because enthalpy itself we're measuring compared to another state. So we're looking at how much the enthalpy has changed from one part of the reaction to the other. So in other words, has energy been given off, or has energy been absorbed? How do I find delta H? I look at the products, so how much energy exists on the product side and how much, enthalpy exists on the reactant side. I compare them, and the difference between the two is going to be my change in enthalpy. And note that if we say that energy is given off, so in other words, energy is a product, like you see in the example below, 2 molecules of hydrogen plus a molecule of oxygen yields 2 molecules of water plus 483.6 kilojoules. That energy is given off, and therefore we have what's called an exothermic reaction. On the other hand, if the energy is required to be put in to the reaction, we would call that endothermic. And we'll get to that in a couple slides here. But that equation, talking about that equation with the energy included, that's called a thermochemical equation. So we can write energy released or absorbed as heat during the reaction. And we want to be aware that in this case we're talking specifically about moles when we use those coefficients. That's not how much energy 2 molecules of water would give off when it's formed. It's how much energy 2 moles of water would require. So the quantity is proportional to the moles. Like we said, those coefficients represent moles. So if I did produce twice as much water, so instead of 2 moles, I produced 4 moles, we would have to multiply that energy amount by 2, just like we would with any of the coefficients. So like I mentioned earlier, endothermic reactions, if we flip that equation around and made it essentially the decomposition of water instead of the synthesis of water, notice it takes 483 kilojoules in some form of energy to break water molecules apart into their individual components, hydrogen and oxygen. So because energy was required to put into the system to make the reaction happen, we call that an endothermic reaction. And it is important to include these states of matter because, for instance, water, a different amount of energy will be required to either break apart, or a different amount of energy is given off when water is formed if it's in its gaseous state versus if it's in a liquid state. So we actually don't usually write those thermochemical equations like I showed. What we're actually going to do is just write the equation as normal and then indicate the delta H as either a positive or a negative number. So in this case, we're forming water. Remember, forming water did give off energy. So the energy was on the product side. So for exothermic equations, or exothermic reactions, notice that the delta H is negative, and because the the energy amount is, the enthalpy amount is on the product side. And it would look something like this, where the reactants have a higher energy, and that energy is given off in the form of heat or light, and then our products are going to have a lower energy state. So that enthalpy is the change we see there. That delta H, that enthalpy change, is going to be negative because our energy went down. On the other hand, with energy going up, we see that we start low with the reactants. We have to kind of pump energy into the system for the reaction to happen. So it's on the reactant side, the energy is. And then our products are at a higher energy state. So we call that an endothermic reaction. And in that case, notice that delta H would, of course, be positive. So here's a big concept we want to talk about, is called the enthalpy of formation. And there will be a reference sheet in your modules to show some different values, because every substance kind of has its own value for this enthalpy of formation. It's basically the enthalpy change that occurs when 1 mole of a compound is formed from its elements in their standard state. So remember, when we say elements, that assumes that things like hydrogen and oxygen, fluorine, chlorine, bromine, iodine, nitrogen, that they are all diatomic. So remember, if I'm forming something like CO2, I'm going to require a C atom in an O2 molecule, not just C and 2 O atoms. Or with water, we actually saw the formation equation of water a little bit ago. 2H2 plus O2 gives me 2H2O. I did not make it 2H plus O. I had to leave these diatomic as H2 and O2. So the standard way we write the enthalpy of formation, or the molar enthalpy of formation, is delta H with a little f to indicate the formation, and there's a little degree sign or 0 up at the top. And again, these are at 25 degrees Celsius and 1 atmosphere, which makes them standard, because otherwise if we're not comparing them at the same pressure and temperature, then there's not really a point in having all those values. So again, I'll provide you with a reference sheet from the book, and these will tell us what each substance's enthalpy of formation is. And remember, it's important to realize that this number stands for 1 mole. I could double that enthalpy if I had 2 moles of substance. If I had 3 moles, I could triple it, etc. But we do want to realize that those values on the table do pertain to 1 mole of the substance. Also note that if there's a very large enthalpy of formation, we have a very stable, and I should say negative, enthalpy of formation. We have a very stable substance. For instance, if we look at carbon dioxide, it's negative 394 kilojoules per mole. It's a very large negative number. It tells me carbon dioxide is pretty stable. Another important thing to note is that elements in their standard state, so like O2, N2, or just like, for instance, aluminum would just be Al, or magnesium would just be Mg. So elements alone in their standard state always have a formation of 0, because there's not really anything to put together to build them up. So that's why carbon and oxygen would form carbon dioxide, because very large negative number is much more stable than the elements alone. So if you have the elements alone, it would prefer to give off that energy and become part of a molecule. The carbons and the oxygens would want to become part of that molecule in effect. On the other hand, compounds with very high positive values, or just positive values in general, tend to be unstable. For instance, hydrogen iodide has an enthalpy of formation of positive 26.5 kilojoules per mole, and we can actually see this reaction happen as hydrogen iodide decomposes into iodine vapor and hydrogen.